Yeah, no, thank you very much, and indeed good morning, and from sunny Arizona, and good afternoon in Europe. My name is Saverio Cambioni. I'm a PhD candidate at the University of Arizona Lunar and Planetary Lab, and as a background, I am a space engineer. I took my master and bachelor in La Sapienza in Rome, and then I decided to move to the US to specialize and complement my background with a PhD in planetary science. And in the progress, I got involved in NASA OSIRIS-REx mission, which I worked mostly on the analysis of thermal data from the asteroid, and using machine learning to understand the sampleability of the surface, so to kind of like see where is the best spot to take the sample that OSIRIS-REx will acquire. And then I got involved in the NASA Psyche mission as a student collaborator for understanding the origin of Psyche and collision history. Next slide, please. My key expertise is, if I have to condense it in like a couple of words, is data-driven planetary science. What I mean by that is that I use data-driven techniques such as machine learning to understand planetary phenomena directly through data. In a certain sense, the common approach is develop a model and then understanding and try to interpret the data. But the data usually have an underlying model that it can be taken, can be understood using machine learning techniques. And I applied this concept mainly to two fields. The first one is remote sensing of planetary data. And the other one is to improve the realism of planet formation, terrestrial planet formation models. And I will be happy to talk extensively in the breaking room about both of these topics. My long-term career goals is to become a professor and open a lab and create a lab in which artificial intelligence is used to solve complex problems in planetary science. And I'm also very interested in Europa Clipper, and I would like to be involved in that in the future. And this is related to a work that I've been doing, trying to merge radar and thermal data to characterize the properties of ice. We applied this work, for instance, to Lake Vostok in East Antarctica, and to kind of like disentangle the effect of temperature and composition on the radar echo power. And of course, knowing the temperature informs about, for instance, geophysical activities going on deep in the ice. And next slide. Next slide, please. Okay, thank you. And so actually, these works that I did so far will be condensed in a thesis, which is indeed titled Application of Machine Learning to Planetary Science. And here I just wanted to show one of the highlights. In this work on the figure on the right, we took a bunch of images of the surface of the asteroid Bennu, which is the target of the OSIRIS-REx mission. And we labeled these images in areas that are safe, that seem to be safe or unsafe based on their roughness. And then we used these images to train a machine learning algorithm to then understand, given new images of the surface, if areas were safe or not, to get closer and for sampling. And actually these highlighted the three new areas on the surface of the asteroid that escaped the previous identification by human operators. Here I just reported the two main papers about the remote sensing, two main papers that I led about remote sensing and planet formation, and I would be happy to speak more about them. In the future, I want to keep working on these both projects and also extending the planet formation part to understand using machine learning habitability of planets. I'm also interested in the use of artificial intelligence, its potentialities for teaching and outreach. So thank you very much for your attention, and I will be happy to discuss anything that I mentioned separately in the breakout room. Thank you very much.
Thank you, Saverio. And up next, Hannah.
Okay, right. Hi, everybody. So my name is Hannah Sargeant. I'm a physics, sorry, no, I'm not. I was a physics student. I'm now a PhD student at the Open University, pretty much ready to submit now. So yeah, originally a physicist. I then trained and worked as a physics and maths teacher, which is still, I still use those skills quite a lot in a lot of the STEM outreach and teaching that I still do. I then went and did a master's in space exploration systems, which culminated in a group research project looking at the infrastructure required for a long-term human presence on Mars. And leading on from that, I then began my PhD at the OU in 2016 in planetary science, but specifically in situ resource utilization. I'll talk a bit more about that in a moment. And I've recently started a one-year postdoctoral research associate role, working on the LoveMeX rover, again here at the OU. Next slide, please. So my research is mostly focused on a particular mission. So it's the Luna 27 mission, which is going to a south polar region of the moon. And it's going to sample some of the regolith into some miniature ovens and then search for volatiles using the Prosper lab. And I was basically given this design and asked, what else can we do? What other experiments can be done with this hardware, with a resource utilization sort of focus? And we realized that hydrogen reduction of regolith was something that we could try. But generally, this experiment is done in equipment that is designed to do it. So it should have a flow of hydrogen gas because it's an equilibrium reaction. But Prosper is a static system. So we were looking at how could we produce pressure gradients to get this flow of gases. And using theoretical and experimental analysis, we showed that this was possible. We could reduce the mineral ilmenite, which is sort of the easiest to reduce, using this type of setup, and we managed to produce, I got a first author paper from that. I then designed and built my own breadboard model of Prosper in the lab to then optimize that reaction, those conditions, which was a success, and wrote another paper for that. And finally, I've managed to use that setup to reduce lunar-like and lunar materials. So I've reduced some Highland simulants, lunar meteorite, and some Apollo samples. So this image on the right is of a grain from Apollo 11 soil sample, and the bright white spots indicate there's pure iron, which means we've extracted the oxygen from the iron oxides in the ilmenite, but also in pyroxenes and olivines as well. Next slide, please. So all of this, mostly from my PhD, but also from my master's as well, I've got these skills. I'll just kind of leave them to one side. But in terms of other experience that I've gained over the years, I did a internship at the LPI in Houston in 2018 with other graduate students. And our project was looking at images of boulder tracks on the moon to try and understand the strength of the regolith there, in particular areas that we want to explore. So I managed to write with the team another first author paper here looking at the traversability of permanently shadowed regions. So can we send rovers to these areas of interest? Some examples of other things I've been able to be involved in. So the ExoFit rover trial, looking at how we can remotely operate rovers, and also some product assurance and safety training with the ESA Academy, trying to understand how to produce spaceflight hardware. And so looking ahead, I'm currently on this postdoctoral research associate role, excuse me, with the LoveMeX rover team. So it's an exploration rover going to a permanently shadowed region of the moon. It will have a mass spectrometer on board, which I'm hoping to work on. But whilst in lockdown, there's not a lot I can do in the lab, so I'm developing some teaching resources that we can use to teach primary school age children about lunar exploration, and hopefully get some publications from that too. But I am looking for a postdoc position sort of early 2021-ish, ideally in situ resource utilization, but generally instrument development and lunar exploration are areas of interest of mine. So if you're interested, or if you've got any opportunities, please do get in touch. Thank you very much.
Thank you, Hannah. Okay, and we have one more presentation this morning from Burke. So get your video going, and we're going to try something a little different with him this morning. We're going to allow him to share. So whenever you're ready, go ahead.
Okay. Well, hello. I'm Berkay Kars from California State University. I mainly do concepts for habitation regarding lunar infrastructure and habitations for the upcoming lunar missions. But today I want to present a particular project that I have been working on with some private sector industries, which is regarding developing a lunar landing and refueling station that can be used to refine lunar ice, as well as lunar crystals that are found and abundant on the lunar soil. But to give you a brief backstory, as you may have heard, back in 2014, the Indian spacecraft Chandrayaan-1 has confirmed the existence of lunar volatiles in form of hydrogen, and this has serious implications because it's the hydrogen and oxygen, which is water, can be used for life support systems as well as developing, which is the main ingredients for rocket fuel, hydrogen and oxygen. So this can be used to bootstrap a lunar economy based on mineral trading as well as production of lunar liquid propellant. Sorry. In order to do that, we analyzed. I mean, you need to have a refinement base up in the moon. So we analyzed and examined different solutions on how we can do that on the lunar surface. In theory, you have three options. You can either build your base on the moon, but then there's a problem of how to assemble and how to get your stuff. There's a problem of chicken and egg dilemma. Which one comes first? So we moved away from building stuff on the moon at this stage. The second idea was to send your stuff to the moon, then assemble them. But then there's also the issue of how you're going to assemble them with the robotics and the time delay that you have. And in the end, we have concluded on going with a third class, which is pre-integrated and pre-assembled, which you build your spacecraft on Earth, you assemble here on Earth, and then you send it to the moon, which provides you the extra reliability opportunities. So the landing pad also has the advantage of providing the lunar dust mitigation, which is going to be a huge issue regarding planetary missions. It sticks everywhere and it's going to damage all the equipment. The goal is, maybe I can show you from a YouTube video animation we did before. That's going to be more clear for you to understand. The idea is to, without any delays in construction or assembly, we want to send the spacecraft to the required or designated landing site and then establish refueling facility, mineral extraction operations. Here we go. I'll show you briefly the how it works. So again, we did the analysis on different methodologies. So again, we send the spacecraft in one piece, preferably from a Falcon payload bay. After it lands, it grounds itself and secures itself to the lunar surface. It has all the requirement equipment built in, including the an electrolysis unit to transform the lunar soil into usable water. And in the end, I was also in the process of designing a LT spacecraft, which works together. In the end, the spacecraft, like what SpaceX is doing here on Earth, it precision lands on this landing pad, eliminating any lunar dust problems. It refuels itself and it then takes out and goes away to do orbital refueling, both for spacecrafts on low Earth orbit or geostationary orbit, as well as maybe some spacecraft that is destined to go to Mars or other planetary bodies. In the end, since this is a closed loop, meaning that your spacecraft goes and comes back and is reusable, the costs are much, much lower than what we're using to launch our stuff from Earth to the space. I wish I had more time to talk this more elaborately or face-to-face, but I wasn't quite prepared as well. But I hope this kind of gives you an idea on what the proposal is. And if you have any questions, I would like to talk to you on the breakout sessions. Thank you.
Thank you, Barke. Okay. All right. So that wraps up our presentations